Hello everyone, welcome back to the HFSS tutorial EC475. Today I'm gonna talk about reflector antennas, which is considered as one of the high-gain and most useful antenna. You can see many applications of this kind of reflector antenna in radio astronomy, microwave communication, and satellite tracking. Today's progress in the development of some sophisticated analytical and experimental techniques in shaping the reflector, also the reflector surfaces, and optimization of illumination over their apertures facilitate to build the aperture and the characteristic that we want and like to maximize the gain of the aperture and the antenna. As you can see in the picture, most popular shapes are the plane reflector, the corner reflector, and the curved reflector, which is especially the paraboloid that we talk about it in the next few slides. So it's been clear that the polarization of the radiation source or the radiation element and the position to the relative to the reflector surfaces can be used to control the radiation properties like a pattern, impedance, or directivity of the overall system. And by the image theory, uh, one can analyze the radiation characteristics with some approximation. Like when we use the image theory, we don't consider the diffraction of the field from the edge, and we consider the whole reflector is the infinite plane, and there is no reflection back from the diffraction order or diffraction radiation of the edges of this reflector. Okay, to better collimate or to focus the energy in the forward direction, the lots of geometrical shape of the plane reflector itself must be changed. The overall radiation characteristic like antenna pattern, antenna efficiency, polarization, discrimination, and so on of the reflector antenna can be improved if the structural configuration of this surface and the reflector surfaces can be upgraded. In this picture, in the left hand side picture, can be shown that as the geometrical optics, if a beam of a parallel rays or the parallel waves in electromagnetics incident upon a reflector whose geometrical shape is a parabola, the radiation will converge or exactly focus at a spot which is known as the focal point. In the same manner, if a point source is placed at the focal point, the rays reflected by a parabolic reflector as a parallel beam and create a parallel beam, which is by using the reciprocity theorem we can absolutely define this phenomena. And as an application, here you can see the largest reflector antenna. There is the world's largest telescope is here in China, in Western China, and it's very attractive to see the application of reflector antenna in astronomy. and just I play it and listen.
In southwestern China, engineers are putting the finishing touches on a grand astronomy facility, a half-kilometer wide dish nestled in the mountains that will gather radio signals from the cosmos. FAST, set to be the world's largest radio telescope, is modeled on the second largest dish in the world, the Arecibo Observatory. Started in 2011, the cost of construction for the FAST facility is estimated to be $180 million. Spherical dishes reflect and concentrate incoming waves from a range of angles, but not onto a single point, delivering a distorted image to receivers. FAST is breaking new ground with a design that pulls a section of the dish into a gradually moving parabola. An array of actuators pull a 300-meter section into a temporary shape. This can be aimed at and track cosmic objects as the Earth rotates. The receiver moves in concert with the axis of the parabola. This brings the benefits of a rotating, tilting antenna to a dish that is firmly fixed in place. Single dishes excel at observing point sources like neutron stars and at scanning a multitude of frequencies in the search for extraterrestrial intelligence. When it comes online, the world's largest radio telescope will also catalog pulsars, as well as probe gravitational waves, dark matter, and a recently discovered phenomenon called fast radio bursts.
Now let's move on to the HFSS and see and simulate a reflector antenna. So here we want to see how to model the dish antenna with hybrid solver. Why hybrid solver? It takes a lot of time and memory resources to model the reflector antenna because of the size in wavelengths. In the finite element method in HFSS, it took a lot of time and sources. It's extremely time consuming to model the reflector antenna and dish antenna just with a conventional method used in HFSS with finite element method. But HFSS allows user to compute the difference port with a different solver, which called a hybrid solver, to achieve a balances between time consume resources and accuracy. So let's see how to design a reflector antenna. Let's go to the HFSS and define a function, equation-based curve for our reflector. Say Z2 for x of underline t, for y of underline t. So just 2 times of underline t, and here 2 times of underline t, and multiplied by underline t, means from the z1 z underline t0, I start from 0 to, let's say, 0.2. Okay, we can it all and see this curve. If we sweep this around the x-axis, we can form a beautiful reflector and dish. And if we put a source, let's say horn source or infinitesimal dipole or something, just plane wave or some excitation source here in the focal point of this reflector or dish antenna, we can just collimate the beam and have a high gain antenna. So because so let's have a change the orientation. Let's go to the relative center and in a X, let's go to distance to 500 millimeter, yes. And for the direction, let's say this one Z, we push Z, okay, and we push Y, okay. Now we have a X, Y, Z, which is the position of our source to illuminate and to feed this structure and this reflector to have a collineate beam. Okay, so as in the last lecture, as we found out how to design a horn antenna, I just used the model and to skip the times and just to see how to use the model in HFSS. Let's go to the component library. In the antenna section, in the waveguide section, we can easily use a horn conical and just to make sure that the target coordination system is relative CS1. Just okay, and now we have a horn antenna, our feeding, and here is the reflector. So also we should define the equation and define the solver for each structure. So we just uncheck the model of the horn of the reflector, and now here just right click on the horn antenna and create a open region, and in a region operation frequency, let's say we have in a 10 gigahertz, and boundary is a finite element boundary integral. Okay, and here there is some trick that we should also use, because there is two kind of solver, and also is not check the model, and just for this model it creates the open region and boundary condition. And if we now use the sign boundary condition and let's say assign hybrid to finite element boundary condition, as you can see here, in here you can see the whole hybrid region and open one and FEB1, and if we click on this, and at that time the open region is expand. So because we don't want this happened, it's back. Okay, and because of this, again let's back, just the open region, and because we don't this happened, just draw a box, especially exactly as same as this box. Okay, and assign the boundary condition here, assign the hybrid boundary condition here, and just delete the open region. Okay, and now by checking the model for the dish and assign the excitation or boundary here, let's say finite conductor, and use the material of aluminum. Okay, and assign a boundary. Again, the integral equation region, assign an integral equation for this hybrid and for this reflector. Okay, and again we can transparent the box to see the antenna well. Now go to the simulation and validate. We need to have an analysis set up. Let's add a solution, 10 gigahertz and maximum number of passes. Okay, 10. All of the minimum number of passes, let's say 3, and the convergence path 2. But because it's a large and time consuming process, it's better to have 1 and just see the result. And the hybrid, okay, I think it's okay. And for because this hybrid model can't solve the sweep frequency, so just disable this frequency and just solve in a 10 gigahertz to see the result. So it validates the result and analyze. So after the analysis and simulation is done, let's see the field and the result of the reflector antenna. And by using the sum horn, you can see the surface current of the reflector, like it, and also see the electric field in this cut and this plane to see how to radiate inside the horn and how to interact with the reflector. So also we can have an animate to see the better, okay, get a better result. Okay, just it by zooming, you can see the field goes through the waveguide and then tapered as a horn antenna and radiate inside the medium and then interact with this reflector and then reflected back and collimated or in parallel wave. If we just see the pattern, if we use the infinite sphere from like this, minus 180 to 180 for theta in a step size like say 10, and for a phi direction we can easily see the result of the pattern in a 2D mode in a dB. Okay, and we can see in the x direction phi equal to 0. Directivity about 40 dB gain, and this is absolutely high gain for this reflector, and they are known as a high gain antenna, the reflector antenna. And also we can see the result of the 2D plane to see the gain. Let's see the far field in a dB, let's say in a primary sweep for phi direction and in a theta equal to 90 degree. Okay, we can see the result and mark it in a point which is the phi equal to 0 in the x direction, you can see we have the gain about 35 dB. Also, we can go to the model. And we can plot the field, radiation field in plotter 1, yes. Scale, let's say 1. As you can see here, all of the beam is go back and reflected back. Let's say 4. Okay. So all of the field is go back, and if we can transparent it again, and we have extremely electric field here and used for lots of application. That means high-gain antenna like radio astronomy, microwave communication systems, and so on. Thank you for your attention. Have a good day.